Okay, everybody. I have a few announcements. First of all, there's a chapter 2 graded assignment, graded problem set. That the deadline was supposed to be yesterday, but I extended it to tomorrow. So it's tomorrow at like midnight, 11:59 p.m. Okay. So, these graded problem sets actually count. They're actually 5% of your grade. So it doesn't make any sense for you not to do them. And I have, there's a chapter 3 graded problem set that's up. I don't know what the deadline is offhand, but in chapter 3, I'm actually giving you, 2 tries instead of 1 try, I think. So let me know if that works, okay? Because I've never done that before. So anyway, and chapter 3 is a bit longer, so you really need to get started on it. You need to finish chapter 2 if you haven't done it, and then chapter 3. These are, opportunities for you to get more points, because you can do them in an infinite almost amount of time. Yeah. It's written down on I just don't have it in my head right now. Okay. And I often look and I see, did everyone do this? And if a whole bunch of people didn't do it, I extend it, but I can't be doing that forever because, the next chapter is already here. We're working on chapter 4 today. So anyway, that's one thing. Another thing is today I can't be in my office after 1:30. So office only until 1:30 today. I'd rather be in my office than going where I have to go, which is the doctor. And the third thing is that we are having an exam on Thursday of next week. And what I like to do prior to an exam is have at least a couple of problem sessions, like extra sessions. And now we have the lab. The lab is open. You're going to be doing a lab in lab today. I think, does everyone know where that is? Where is it? Oh, so the lab is in, all right, come on, I'm talking now. Whipple 106, right? Is that right? I'm pretty sure. Yeah. Whipple is near that big parking lot. Whipple. Where's Whipple? I don't know.
That direction.
You know that when you come on campus, there's the pit parking lot, then the next parking lot on the right before you get to the main campus. There's a long parking lot that goes way down the width of the whole campus. Do you know what I'm talking about? You know where they have the place where they take care of the little kids, the daycare. It's right near there. Yeah. Okay, so lab is in Whipple. I think it's 106. It looked okay. I went and looked at it on Friday. I was pleasantly surprised. When I'm making announcements, it's really annoying when people are just chatting away. So, do your chatting before 10, okay? So anyway, so I won't be in my office today after 1:30. So that's one thing. Do your chapter 2 and chapter 3 graded problem set. I extended the deadline on 2. We have an exam on Thursday next week. Okay, that's going to be, everything through what we cover this week. So there's a lot on it. And I would like to have some problem sessions. I was thinking maybe of doing this. I could do it on Friday, although a lot of students aren't around on Friday. I could do it on Monday. I could do it, what? Yeah, I mean, I'll do a few of them. I could even do a Zoom over the weekend or something. I can't do it every single day. I thought Tuesday after class, I know some of you have lab, but I could also do it after lab. So I'm going to talk about it on Thursday, and maybe we'll come up with some dates. So think about what's good for you. Okay. I'm also going to give out some problems, a problem packet of problems that you should study. Okay. So that's, I'm going to give that out next time. And I'll post it. All right. So I have a big handout. This is, believe it or not, this handout is only for the first half of chapter 4. Okay, chapter 4 has a lot of stuff in it. And the book is the book doesn't spend a lot of time. So especially in the second half, this is only part 1 of chapter 4. In part 2, I have a lot of information, like readings about chemical reactions, so you should read that when you get it, because the book is very, it goes through chemical reactions like at the speed of light. Okay, thank you. So okay, so getting on with what we're going to do today. The first order of business kind of is to get used to some of the language of chemical reactions. So we have a little new vocabulary, some of which I think should be pretty familiar to you, like the word reactant. A reactant is something that reacts in a chemical reaction, okay? And what is it called, the thing you get at the end of the reaction? A product. This is what forms. We often use phases in chemical reactions. So we will write, for example, H2O liquid, or we'll put NaCl aqueous. What does that mean when you see NaCl aqueous? Yeah, it means it's a solution. Okay. We could have all kinds of different, we'll have O2 gas. Okay. Another thing that you have to know is if I say something, here's a few things, like how would you put this? Zinc metal. If it says zinc metal reacts with, something, how would you write that in a chemical reaction? Well, that's just zinc solid, okay? Because all but one metal are solids at room temperature. Anyone know what that metal is? That's liquid at room temperature? Mercury, yeah. And we don't study any reactions of mercury, so all the metals are solid. Okay, if it says oxygen in an equation, oxygen reacts with blah blah blah, how are you going to write that down in a chemical reaction? What is the form that oxygen takes in the real world? It's O2. So you have to know that it's a diatomic. So you need to memorize the Bro-Finch. Remember Bro-Finch, this C here is chlorine, not carbon. These all exist as diatomics. So if it says bromine, you have to write Br2. It says iodine, you have to write I2. If it says chlorine, it's Cl2, hydrogen, H2, etc. Okay. And you also need to know that oxygen is a gas, but I think that all of us know that. But it probably would say oxygen gas. Anyway, another commonly used term when you're talking about basic chemical reactions is precipitate. Precipitate, which has a very different meaning from, like we say, it's precipitating, it's raining outside, but that's not what it means here. A precipitate is a solid that forms when two ionic compounds react in solution and form a product. I know it's a long-winded explanation, that is not soluble, that does not dissolve in water. So you mix these two clear solutions together and you see, at least after you wait a while, you see cloudiness. It'll be cloudy when you mix them together. So two clear solutions, it's cloudy. And then if you wait, you see solid on the bottom. That solid is the precipitate. And another terrible chemistry joke is people used to say all the time, like in the 60s and 70s, they still say it. If you're not part of the solution, you're part of the problem. But the chemistry analogy is if you're not part of the solution, you're part of the precipitate. I know. Ugh. Oh, well. All right. So with all this in mind, let's take a look at the first activity for this chapter 4, which I just gave out. So this is really like translating sentences into a chemical equation. And then we will have to balance the chemical equations. So zinc metal, this was one of the first things I just told you. So that means zinc solid reacts with oxygen. So what would I put here for oxygen? O2 gas to produce solid zinc oxide. So we know it's going to be solid, but what is the formula for zinc oxide? How do you figure that out? You know, this is something we actually learned last week, right? Zinc always is 2 plus, oxide is always 2 minus. So what is the formula for zinc oxide? ZNO, one of each in one formula unit. That's the challenge that balances the charge. So this would be ZNO solid. So we would have zinc solid plus O2 gas goes to ZNO solid. So the first thing I'm trying to get you to do is to translate vocabulary into chemical equations. The second part of the chapter, which we will do later, and I cover it in a different order than in the book, I will be asking you to come up with the products, but we're not there yet. Right now, we're just getting the language straight. And now this brings me to another part of all this, which is this equation is not balanced. Let me shut that light. I forgot. Yeah, look at this. You have one zinc on the left and one zinc on the right, but you have 2 oxygens on the left and only 1 on the right. Now, what you cannot do is you cannot change the formula. You can't make this ZNO2. Don't do that, because that would be a wrong formula. So formula is like, you can't change it. That's the correct formula. There's only one correct formula. So there's only one weapon that you have to balance this equation, and that is to put what we call coefficients in front of the entire formula. So how am I going to get 2 O's on this side? I'm going to put a 2 over here. Okay? Yeah. So when you do this, a lot of times you mess something else up. So it's kind of a back and forth operation balancing. So I went over here and I put the 2 to get my 2 oxygens now, but now I have 2 zincs on the right and 1 on the left. So I have to put a 2 here. And now I have 2 zincs. And notice I have 2 oxygens because this 2 gets distributed, right? I have 2 zincs and 2 O. So when you have a number, a coefficient in front of a formula, it multiplies everything in that formula. Every atom gets multiplied, okay? So that's the first balancing example. And at the end, what do is you look and you count up each of the elements, and you see if you have the same number of atoms of each type on each side of the equation. Okay, so let's do the second one. Now here we got to write some formulas, some more complicated formulas, all right? So barium chloride. What is the formula for barium chloride? Where is barium in the periodic table? Really sad we don't have a periodic table, but take out your periodic table. You should have one. So barium is in group 2 or 2A. So it has a +2 charge. Chlorine is -1. So to balance the charges, we would have to have 2 Cls and 1 barium in a formula unit. So that means this formula is BaCl2. And you have to get that right. If you get the formula wrong, the equation is going to be wrong. So aqueous barium chloride reacts with aqueous sodium carbonate. Okay. What's the charge of sodium? Someone else. Yes. +1, Na plus. Carbonate. Now, what's carbonate, first of all? Yeah, it's one of those. You got to look it up. Well, but what is the formula of it? CO3. So you look that up on the chart, and it tells you that you're going to have 2 sodiums to balance the 1 carbonate. So the formula will be Na2CO3. And I'll put an AQ here. And this goes to produce, okay, here we go, a solid precipitate of barium carbonate. Barium again is 2 plus. Carbonate, we already know, is 2 minus. So the formula is BaCO3, one of each in a formula unit. So BaCO3, and that's solid, plus aqueous sodium chloride. I think we all know that's NaCl. Okay. So now we have to balance this. How do we do that? So the first of all, the first thing I look for is something glaring, something that where there's 2 on one side and 1 on the other side. And another thing is, and this is a hint that is very good to use, that look, if you have polyatomic ions, okay, so here you have a CO3, and here you have a CO3. So there's no point in breaking them up to 1 O and 3 Cs. You could consider the CO3 as a unit and balance. If they're on both sides, then leave it that way. Don't start breaking them up, okay? So you have 1 carbonate on this side and 1 carbonate on that side. So that's not going to help us with the balancing. Okay, and I leave out the charges when I do that because the electrons don't change anything with the balancing. But what is the one, there's a couple of things that are, yes. The chloride. Okay, so I have 2 Cls here. So what do I have to do here? Put a 2, but now I have 2 NAs. But I need to, right? So that's what, when you're doing it right, that's what tends to happen. Is you start putting in a few numbers and the other numbers all work out. If you start to put in a number or 2 to balance and the numbers aren't working out, it's either that you have something where you have to double everything, or it's that you're doing it wrong. So let's continue with some more examples. So are we done here? We have 2 Cls on the left. Not yet. And we have 2 Cls on the right. We have 2 sodiums on the right. Okay. We have a carbonate on each, and we have a barium on each. Okay. So we're all set. We have 1 barium, 1 barium. Okay. So we have the same. So we're done. So this is the balanced equation. All it needed was a 2 in front of the NaCl. Okay. Let's do another example. Aluminum metal. Okay, now here I will take your hand out and look on the back page. Okay, the back page is a list of acids. Okay. The top is what we call the 6 strong acids, and the bottom is weak acids. Okay. And so you can get the names from there. So this says aluminum metal reacts with aqueous hydrochloric acid. So what's the formula for hydrochloric acid? HCl, and it's aqueous. Aluminum metal is just aluminum solid to produce. Now, when it says hydrogen gas here, what does it mean? What do I write? Do I write this? H2. It's a diatomic, and you need to know that, or you're not going to get the balanced equation right. Okay. And now we have aluminum chloride. So what is the charge of an aluminum? Remember, it's in a weird group. It's in group 3A. So it's like you have your two groups, and then you go all the way past the transition metals to group 3A. Yeah. So it's +3. And so it's Al 3+. Okay. And chloride is Cl-. So we know we need how many chlorides here? So the formula is AlCl3, and it's aqueous. So now we can write the equation. Aluminum metal reacts with aqueous HCl to give hydrogen gas plus aluminum chloride, aqueous. Okay. So what are we going to start with here? What's something that is glaringly wrong? Chlorine. We have 3 here. So what do I have to do here? Right, that's right. But that gives me 3 hydrogens here and 2 hydrogens here. So when you see that, you now what you're thinking is, how am I ever going to fix this? So a good idea when this happens is you multiply by 2. So if you multiply by 2, you would get 2 Al. This will become 6 HCl. So multiply by 2. And that would give you, so you multiply what's on the left by 2, and now you can see that you need 3 H2s. And now what about the AlCl3 here? You're going to have to put a 2 to match the 2 here. And lo and behold, 2 times 3 is 6. That's how many chlorines you have. And you have 6 on the other side as well. My pen is already stopping, so that's not a good sign. Okay, so you see what we did was we ran into a problem. So we doubled everything on the left. We figured out what number we needed for the hydrogen based on the 6 hydrogens that we have here. And it worked out. So now I could just see if I have everything right. 2Al, 6Cl, 2Al, 6Cl, 6 hydrogens, 6 hydrogens. So I'm done. Okay. So I'm going to do one more, and then I'm going to ask you to do the next 3. And we'll run into some problems, and then we'll get back here and I'll try to help you with them if you have a problem. So the next one is gaseous carbon monoxide. Okay. So carbon monoxide, what is the formula? CO, gas, reacts with oxygen gas to produce carbon dioxide gas. Okay. So you see I have a problem here. What's my problem? I have 3 O's on the left and 2 O's on the right. So what's the solution? Multiply by 2. Here, we multiply the first one by 2, and we're done. Because we have 2 carbons, 2 oxygens, almost done, 2 oxygens. So what do I have to do here? Right, because then I have 2 carbons and 4 oxygens. See how that works? So that's done. Can be a little, you get used to it, all right? So anyway, I'm going to ask you to do 5, 6, and 7. And let's see, I'm going to tell you for 5 to balance the oxygen last. And don't forget that you have an oxygen there. Okay, so burns in oxygen simply means reacts in oxygen. Okay, so you'll start with C2H6O liquid, this is ethanol, plus O2 gas. And you can finish that and then do as far as you can with these 3 examples, and I will come around. All right. Anyone need the handout? What are we doing here?
I actually so at the end when it's final corner, let's go back to this one. The plan is like this, right? That's it. Okay, I just want to make sure that that's from. Okay. Yeah, I know. That's what I'm looking at. Oh, yeah.
carbon first and then the hydrogen. And then the hydrogen. Now you have a total of how many O's on the right?
Oh,
That, yeah, and now there's one over here. How many do you have to balance? Okay.
thanks.
The hardest, one of the hardest things. So like, yeah, which one's lost, right? Oh. Honestly, if the three is one.
We'll start to like, I took an out of I there. I like this cover study. That don't not study your notes for a class, 3 or 4 weeks class. It'll go back, so that's why it's fresh. Oh, yeah, yeah. How do you know, right?
Because I have a paper.
Oh, okay.
Okay. But, yes.
Yes, yeah, plus. Yeah. You can't be increased plus PaCO2. And then BaNO3, but that's in parentheses number 2. Because it's in order to balance that, you need 2 NO3s. Because the barium's and then it's 2 AgCO. Yeah.
Is it silver one fluoride?
Yeah, but the 2 is coming from the balance. Yeah, those starting. Because so on the right side, there's
Oh, it's a 2 fluoride. You have to
yeah,
have a 2 silver.
yeah.
Okay.
Oh, I didn't. Okay, yeah, there's silver 2. Yeah. Right.
Silver is plus 1.
So,
Here, you have
but-
2 fluoride.
Yeah. You know? No, that's one.
Yeah, silver is all good.
Yeah, okay. I think silver is bad. Oh.
So what you said is that you put a 2 here.
Yeah. So basically you go back and forth, right? So.
I was just missing.
Yeah.
That's what I was thinking.
Yeah. First part's the part.
Yeah, if you get up to the one, nitric acid is an acid chart, the acid table that I gave you, the acid sheet. So you can look up this one.
Is it MG3, the deal?
Oh, this one.
Yeah.
I got stuck on your things as well, so I'm gonna.
That in a deal for us.
Yeah.
The very first.
I think they're a deal for you.
Like.
Oh, yeah. Sorry.
Yeah, I just want to make sure. I mean, energy.
Oh my God.
Yeah.
And my B did have this.
Yeah.
So you can leave those like that, so empty of those.
That's what energy. On which side?
Right.
Yeah.
Oh, I'm with-
Yeah, that's.
Oh, I see. Yeah, you have. Yeah. Yeah, now it's not very creative. I was like.
So.
I'm gonna go over these. Now, now's really the time to ask all your questions while I'm going over this. If you don't understand something, please ask me. Okay, so here we are. This one looks pretty simple, but actually it's pretty tricky in a way. So this is what you do when you have, this is called a combustion reaction. If I took a little ethanol and I put a little wick in it and I lit it, it would be burning the ethanol. That's what this equation is. Combustion, burning, same thing. The key is that you leave oxygen for last. And also, you're only trying to balance one element at a time, okay? So let's pick carbon. We could pick carbon or hydrogen to do first. Let's pick carbon. I know I need to have 2 carbons on the right, so I put a 2 here. I know this is affecting the number of oxygens, but I don't care right now. I'm leaving oxygen to last. What about hydrogen? I have 6 hydrogens here, so what do I need to do here? I put a 3. And now I have oxygen is the only one left. Why do I leave oxygen to last? Look at this equation. Oxygen is everywhere. If you do oxygen first, you're going to change everything else, right? So don't try to do oxygen first. All right, so let's think about the oxygen. How many total oxygens do we have on the right-hand side of this equation? Right, we have 3 O's here and we have 4 O's. You see, you have to distribute this too. So you have 4 oxygens here and 3 here. That's a total of 7. So I have to get 7 oxygens on the left side, and I have 1 over here. So that means I have to put a coefficient in front of this oxygen that's going to take care of 6 oxygens, because I have 1 over here. So that means I have to put a 3. Okay, does that make sense? Yeah. All right, so that's balanced. And I did notice that some of you get these formulas perfectly. Usually those are the people that have the periodic table next to them and the polyatomic ion chart next to them. So that's what you need to do this. If you haven't memorized all those ions, which you don't have to, you need the chart, because a lot of you are trying to balance equations when the formulas aren't right, and that's going to be a problem. So let's look at this. Silver nitrate. Silver, if you look at your transition metal ion chart, it tells you that Ag is Ag plus. It also tells you on the polyatomic ion chart that nitrate is NO3 minus. So you only need one of each. So this is silver nitrate, AgNO3, aqueous, plus an aqueous solution of barium chloride. We've talked about this formula already earlier. Barium is in the second group of the periodic table, group 2 or 2A. Its charge is +2. Chloride is in group 7 or 17. It only needs one electron to be like a rare gas. So it's Cl minus. So you need 2 of these for one of these. And the formula is BaCl2. So aqueous solution of barium chloride to produce aqueous barium nitrate. So for barium nitrate, what's the formula going to be? That's right. You'll need 2 of these for one of those to balance the charge. Plus a precipitate, that means solid, of silver chloride. Ag is +1, Cl is -1. You need one of each to give you AgCl. Okay, so now we have the formulas. Once you have the formulas, you don't change the formulas. Okay, so how do we balance this? We look for a glaring error, something where you have 2 on one side and 1 on the other side, or something like that. And so there's 2 things you could do. You could do the nitrate, because remember I said that if you have a polyatomic ion that's the same on both sides, just balance the nitrates, keep it together. Don't start breaking it up into N's and O's. That's too much trouble. So I see I have 2 here, and so I need a 2 here. But now I have 2 silvers as well, so I'm going to have to put a 2 here. Uh-oh, now I have 2 Cl's, but look, I have 2 Cl's on the left. So it's a back and forth kind of effort. You put a number, you see how putting that number affects the other number in that formula, the other element. You go back to the other side and balance that one. And if you did it right, in the end, you'll get something that works out. Like you'll see, oh, 2 Cl. Oh, good. I have 2 Cl's here. Perfect. And my bariums are balanced. So on the left, I have 2 silvers. On the right, I have 2 silvers. I have 2 Cl's. I have 2 Cl's. I have 2 nitrates. I have 2 nitrates. And I have 1 barium. Okay, I don't even bother with the charges when I'm doing balancing. Okay. Is there a question about that? Yeah, so you know what this means is that you really have to know how to do the formulas. If you don't know how to write formulas, you can't really do this. Okay, sodium phosphate, aqueous sodium phosphate. So sodium, what's the charge? Phosphate. Oops, PO4 3 minus. So you'll need 3 of these to balance one of those, and your formula will be Na3PO4, so aqueous sodium phosphate. Reacts with aqueous magnesium sulfate. You can see that you only need one of each. To produce a precipitate, okay, now we have magnesium phosphate. So magnesium is 2+, phosphate is 3-. So this is where it's good to use the crisscross method. Mg3PO4 2 gives you the formula. So in one formula unit, you have 3 Mgs at 2+ each, and 2 phosphates. So you have +6 and -6. And so your formula is Mg3PO4 2. And that is a precipitate, so that's solid. and aqueous sodium sulfate. What's the formula for sodium sulfate? That's right, because sodium is +1, and there's 2 of them to balance the -2 of the sulfate. Okay, now how do we balance this one? Well, now here's a situation where, okay, let's start with something. Let's start with the magnesium. We have 3 on this side. Let's put a 3 there. So that means I need 3 sulfates. So I have to put a 3 here. That means I have 3 sulfates, but now I have 6 sodiums. So what do I do over here? Put a 2, because that's going to be 6 sodiums. That means 2 phosphates, but I have 2 phosphates. So it's back and forth and back and forth. And I didn't have to start there. I could have started somewhere else. You can, if he's asking, should you always treat a phosphate as a PO4 on both sides? I mean, should you ever break it up into P's and O's? Sometimes you have to break them up, and the next example is going to show you that. Okay, so here's 8. Okay. So now calcium carbonate, we have Ca2 plus, CO3 2 minus, so that's CaCO3, just one of each in a formula unit. So solid calcium carbonate. Okay, here you have to use the chart that you're given. Nitric acid is HNO3. And that's aqueous, to yield aqueous calcium nitrate. Okay, so calcium is 2 plus, nitrate is 1 minus. So I'm going to need 2 nitrates to balance the calcium. So I'll have CaNO3, 2. Okay, now here's the kicker. We have CO2. I want to have room here, plus H2O, liquid. Oh, CO2 is gas, sorry. Okay, squeezed it in. All right. So back to your question. The question I was asked is, do you always keep polyatomic ions together? Now here you have a carbonate on the left, but here you don't have a carbonate. It's broken down to something else. It's changed. So you can't do it here. Okay. But like we always do, we leave the oxygen for last. Okay. So let's balance this. Yeah, the first thing you see is you have 2 hydrogens over here in the H2O. So you're going to have to put a 2 over here. But that means 2 nitrates, but that's good because you have 2 nitrates here. So far we have 2 hydrogens on both sides. We have 2 NO3s on both sides. Okay. We have 1 calcium. And now we have to deal with the carbonate. So now we have to see, okay, we have 1 carbon here. We have 1 carbon here. And we have, okay, we have 3 O's from the carbonate. See, I already balanced the NO3, so I'm not counting those. And you could see I have 2 here and 1 more here. So I have 3 O's not in the 3 O's that were from the carbonate. But what you don't even know if how it got there. All you know is that these O's in here are balanced, and so are these. So you're only balancing these 3 to get 3 over here, and you have 1, 2, 3 over there. So this is a little trickier. And if you prefer to break it all up and do the balancing that way, that's okay too. But I'm just telling you the tricks of the trade that make it a little bit easier to do. So that equation is balanced. All you needed was a 2 here. All right, so
Even if the CL is part of that compound on the left, it still balances out the oxygen to the H2O on the right. Because it's an oxygen.
well, what I did was I balanced the oxygens that were in the nitrate, right? I balanced the nitrates. So the oxygens and nitrate are all taken care of. So the only oxygens I'm balancing at this point are the 3 from the carbonate. So that means that I have to have 3 other oxygens that aren't in the nitrate.
So we don't have to look at the one compound, that's the one single thing, like the.
No, you can't here because you don't have CO3 on the right. So when you have the same ion, polyatomic ion on the right and the left, then you should keep it together. But if you don't, then, you have to balance it some other way. Yeah. No. Question? All right, so I'm going to move on. Now that we have some little bit of familiarity with equations, I'm going to, since at the end of chapter 3, what we did in chapter 3 was we did a lot of mole to gram, gram to mole conversions. And now what I'd like to do is show you how to relate the mass of different participants in the reaction. So the participants are the reactants and the products. So what I would like you to do, what I would like us to be able to do at the end of today is to figure out, like, if you start with 5 grams of a reactant, how many grams of product are you going to get? No, not necessarily. Because you have more than one reactant and more than one product. If you only had one reactant and one product, yeah, conservation of mass tells you that. But that is most often not the case. So what we're doing here really is relating. So this is how to relate the masses of reactants to masses of other reactants or to products and to products. So for example, like I just said, suppose you want 5 grams of a product. How do you know how many grams of reactants to use? Okay, so this is like mass relationships in chemical reactions. That's really what we're talking about now. Okay, so doing this, figuring this out, you have to start with a balanced chemical equation. If your equation isn't balanced, this isn't going to work. Okay, so for example, if I have silver nitrate and zinc, gives me zinc nitrate plus silver metal. Okay. And I balance it, so I have to balance it. That means, let's see, I have 2 nitrates here, so I have to put a 2 here. Now I have 2 silvers, so I have to put a 2 here. Okay, so my silvers are balanced. I have 2 on each side. My zinc is balanced. I have 1 on each side. My nitrate is balanced. And that's all there is. So I'm all balanced. So I have this balanced chemical equation. And when you don't have a coefficient, it means it's a 1. And I'm writing that because I want to tell you what this means when you have an equation like that. What these coefficients give you are how the moles of reactants and products react with each other. Okay, so we have a 2 to 1 to 1 to 2. So 2 moles of silver nitrate react with 1 mole of zinc to produce 1 mole of zinc nitrate plus 2 moles of silver. So these coefficients give you the mole ratios of how these things react with each other. And this brings us to a topic which is called stoichiometry. And stoichiometry is a kind of a hard word to say, but we use this all the time. Stoichiometry comes from the Greek, stoichio means element and metry means measure. I don't know how that gets you to stoichiometry, but it does. And we call this unit stoichiometry, and these coefficients here we call stoichiometric coefficients. The 2, 1, 1, 2 are stoichiometric coefficients, and they tell us how the moles of everything in this chemical reaction relates to everything else in the chemical reaction. So we really don't call that this ratio, the stoichiometric ratio of reactants to products, we usually call it a mole ratio just because it's a little simpler. So let me write it down again. I'm going to write it without the phases for simplicity. And this is 2 to 1 to 1 to 2. Okay. And so the mole ratio is 2 to 1 to 1 to 2. And so what that means is that if 2 moles of silver nitrate, they will react with 1 mole of zinc to produce 1 mole of zinc nitrate and 2 moles of silver. But what if we started with 4 moles of silver nitrate? We're not going to always start with 2 moles or 1 mole of something. 4 moles will react with 2 moles of zinc to give 2 moles. You see, so the ratio is the same. 4 to 2 to 2 to 4 is the same as 2 to 1 to 1 to 2. But if you start with 4 moles of silver nitrate, you'll end up with 4 moles of silver. Okay. For example, if you started with 8, you'd have 4, 4, and 8. It's the same mole ratio. Okay. So the ratio of each of the moles of each of the participants in the reaction to any other participant in the reaction is the same for a given chemical equation. So for example, I have 2 moles of AgNO3 to 1 mole of zinc. Okay, so this is a reactant, this is a product. And I also have that 1 mole of zinc relates to 2 moles of silver nitrate. So if I end up with 1 mole of zinc, it means I started with 2 moles of silver nitrate. I could also relate a reactant to another reactant. So for example, with this same equation, I could have 2 moles of AgNO3 to 1 mole of zinc. Actually, zinc is not a product. Sorry, zinc is another reactant. So I already did the other reactant. Sorry about that. Now I'm going to do a reactant and a product. This is a reactant. This is a product. 2 moles of silver nitrate yields 1 mole of zinc. So we have a stoichiometric ratio of 2 to 1. And of course, we could write it the other way if we needed to. So what we do, these are called stoichiometric ratios, or simply mole ratios. Okay. And the reason we write it like this is because I've been showing you, hopefully teaching you, how to do dimensional analysis. And now if I want to go from, say, moles of a reactant to moles of products, all I have to do is use that mole ratio. Okay. And with dimensional analysis, as you know, if you want to get rid of something, like say you have grams and you want to convert it to moles, you put the molar mass so that the grams cancel and you end up with moles. So we're going to do it so that the right thing cancels. Yeah, let's see. Because zinc nitrate is a product and silver nitrate is a reactant. Well, what I'm saying is you could use either way. I could use this way. It depends what I'm starting with and where I want to get to.
So on your react,
Left. No, the reactants are on the left and the products are on the right. The products are what form. The reactants are what react.
The ratios you mix those three, or their ratio.
Yeah, they're just saying how many of one to how many moles of one to moles of the other. I think if I do an example, it might be helpful. So let's go to this stoichiometry 1, the first activity 2, okay? So we have 2H2 plus O2 goes to 2H2O. I like to put in a 1 here. Just to make sure everybody knows what these coefficients are. So my stoichiometric coefficients are 2, 1, and 2. If you don't see 1, it's a 1, okay? So now it says how many moles of H2 would react with 15 moles of O2? So you start with what you know, and what you're given is 15 moles of O2. And now this is really practicing with those mole ratios. So where do I want to go and where am I coming from? So, but I want to get rid of moles O2 and I want to end up with moles of H2O, because how many moles of H2O would be produced? So I would have, right, because there's 2 moles of H2O to 1 mole of O2. And now my moles of O2 cancel and I get 30 moles of H2O form. So this is your first example of a stoichiometry problem, okay? So now let's do the second one. Because here we went from moles of a reactant to moles of a product, but we could also go from moles of a reactant to moles of another reactant that would be needed to react with it. So if I start with 24 moles of H2, how many moles of H2O would be produced? I guess I'm just going from a different reactant to a product. Again, here it's 2 moles of water because the coefficient is 2. And what do I put on the bottom here? Right, H2. So these stoichiometric coefficients between the H2 and the H2O are the same, okay? So that means it'll be the same mole amount. And you can see that the 2's here are going to cancel. And you will end up with 24 moles of H2O form. Okay. Let's do this one. This one has a little more complicated set of, did you all get that down? So this is a little bit of a more complicated equation because I have some, numbers that are a little more difficult, but still not hard. So it says, how many moles of Fe react with 1.32 moles of O2? So now it's like, how many moles of one reactant are needed to react with 1.3 moles of another reactant? So it can relate reactants to reactants as well as reactants to products. So I want to get rid of moles of O2. So I put it on the bottom, so it's going to cancel. And it's 3 moles of O2 relate to 4 moles, because that's the coefficient of Fe.
Are we always? Numbers
What numbers?
or
I could ask you to balance the equation first.
Okay, and then we would always use that to, it just seems too good to be true.
Well, let's not kick a gift horse in the mouth, okay? It's really not that, it's not that crazy. All right, whatever you might have heard about chemistry, I don't know, but so here now you're actually, you're multiplying. This one you might have had trouble doing it in your head, right? Because it's multiplying by 4 and dividing by 3. Pen doesn't want to work. What else can I tell you? Well, pen catches up. So this comes out to 1.76 moles of Fe. That's what's needed. Okay. And now, how many moles of Fe2O3? Let me write the equation again. 4 Fe plus 3 O2 goes to 2 Fe2O3. So now we're asking how many moles of a product form when this many moles of O2 react. So I start with the same number of moles of O2. That's what's given. Start with what you know. Start with what you're given. So what am I going to put in here? What goes on the bottom? 3 moles of what? O2. I want to get rid of moles of O2. Yes. And what goes on top now? 2 moles of Fe2O3. Okay. So that comes to 0.880. So what you're doing is you're multiplying 1.32 by 2. And you're dividing it by 3. All right, we'll have to do that later. Okay, now we're going to bring grams into it. So we have the same reaction. And we've done moles to moles. We've gone from, moles of oxygen to moles of iron, moles of oxygen to moles of products. But what I originally said here was we're looking for mass relationships in chemical reactions. So here is a different question. In the same reaction, how many grams of Fe react with this many grams of oxygen? So here we have a couple of extra steps because we cannot directly relate the grams of something in a reaction to the grams of something else. So let me write that down. You can't directly go from grams of O2 to grams of Fe, because what we have is a mole ratio. We do not have a gram ratio. We have to go through moles. So, but we know how to go from grams to moles. So our strategy is going to be to go from grams of O2. This is our strategy. We're going to go to moles of O2. And then where are we going to go from there? What are we trying to get? We're trying to get grams of Fe, but we can't get there directly. So we're going to get first moles of Fe, and then we're going to get grams of Fe. So this type of problem is a grams to moles to moles to grams problem. It's kind of similar to when we were finding the mass of, say, sodium and sodium chloride, but Maybe you don't remember that, but anyway. So what do you do for each of these arrows? How are we going to go from grams O2 to moles O2? What are we going to use there? How do you go from grams to moles? You use the molar mass of O2. How are we going to go from moles O2 to moles of Fe? No. The mole ratio. Okay, from the balanced chemical equation. And then how are we going to go from moles of Fe to grams of Fe? We're going to use the molar mass again, a little differently. One of these is division and one of these is multiplication. Okay, so now let me show you how to do this. Okay, so we start with what we know, 56.5 grams of O2. So now I'm going to convert that grams to moles. So what do I need the molar mass of? The molar mass of O2. It's 2 times 16. 32. This is important. O2 is not O. There are 2 O atoms in O2. So you must put, and 32 grams in 1 mole. This 32 grams per mole means 32 grams over 1 mole. Okay? It's not, that's the proper way to write it. So it's 32 grams per 1 mole. And I write it on the bottom so that my grams cancels. Grams of O2. And I want to be very specific about my labels because now I have to go from moles to moles. So what am I going to put on the bottom here? Let's look at that equation again. What's the coefficient of the O2? It's 3, yes. So I want to get rid of moles O2. The thing I want to get rid of goes on the bottom because it'll cancel. This is the coefficient. So what goes on top? What do I want to get to? Moles of Fe. And what's the coefficient of the Fe? Which I can't seem to scroll down. 4. It was there. 4 moles of Fe. This is again, use the coefficient from the equation. And now, oh, I was going to do this one step at a time. Yeah, I mean, maybe that's too much to do it all at once. I'll do it all at once, then I'll show you how you could break it down. And then for iron, 1 mole of Fe, the molar mass of iron is 55.85 grams. And so my moles of Fe cancel. So you can do this all at once. But maybe I really shouldn't. I was going to do it the more basic way. So at the end, you have to do this calculation to get, and what you end up with is grams of iron, which would be 131. But let me break it down again, because I didn't want to do that to you so fast. You can do it a step at a time. So if you started with 56.5 grams of oxygen, 1 mole O2, 32 grams. So that gives you 1.7 7 moles of O2. Okay, that's what you would get if you did your calculation here. And now to the next calculation. We have 1.77 moles of O2. Again, we look at the balanced equation and we use the coefficients. we want to end up with iron, so it's 4 moles of iron to 3 moles of O2. So that comes out to 2.35 moles of iron. These cancel. And then 2.35 moles of iron, which we're now going to convert to grams using the molar mass of iron. So I'm just doing the same problem over again. Gives you 131 grams. So I recommend that you learn how to do it the quick way, which is to do it all at once, but it might be a lot to digest at this stage of the game. Okay. Okay, so let's see. So why don't you do that work on the handout of the day? Number 1 should be pretty straightforward. And number 2 is an example like the one I just did. Don't do this thing down here. Just do the HOD. For number 2, I'm going to calculate the molar masses you need for you. So the molar mass of NH3 is 17. .04. And I will answer any questions that you have with this handout of the day. I'm not trying to stump you. If you are done, then go on and do, what will we up to? 4A. That. We did 4, we did 3. Oh, we could do 3B. Did I do 3B? Do activity 3B.
I'm doing it one day.
Okay. And activity 2, 1.
If you're going to put walls, got that.
All right, you know what? I'm gonna go over this. Even though I'm collecting it, but you get to hear you. All right, come on, I got a few minutes, so let's quiet down here. All right. We start with 21 moles of H2. So you start with what you know, 21.0 moles of H2. Okay. And now in here is where you put your stoichiometric coefficients that relate H2 to NH3, because that's, oh, no, sorry. What is it? Start with 20 moles of, oh gosh, I wrote this wrong, didn't I? What was it supposed to be? How many? Oh my God. How many moles? Sorry. Okay, so it's 3 moles of H2 yield 2 moles of NH3. So it comes out to 14. Now somebody could have told me that. Well, you didn't try hard enough. Okay, so now this one. All right. So we start with what we're given, what we know. So what is our strategy here? We're gonna, okay, a lot of people wanted to go through oxygen. They wanted to go from grams NH3 to moles NH3 to moles of oxygen. But oxygen is really not involved in this problem. It would have to be assumed that the right amount of oxygen is there and reacts. If you started with 15.1 grams of NH3 and it all reacts, how much product H2O are you going to get in grams? So you wouldn't bother with the oxygen. First thing we do is we convert grams to moles, okay? So we use 17.04 grams of NH3 to 1 mole of NH3. And I'd like to do this all at once, but I wrote in there, so I can't. 15.1 divided by 17.04 is, yeah, that's wrong. Yeah, 0.886, as you said. So now you have 0.886 moles of NH3. And now you're going to moles of water. So now is where you use those coefficients. So you have 4 moles of NH3 to 6 moles of H2O. And when you do that arithmetic, you get 1.33 moles of water, which if you did it all at once, you wouldn't even have done these intermediate calculations, which is perfectly fine. And now, what do I put up here and down here? For what? I saw a couple of you didn't put 1 mole down here. you put in the coefficient from the equation. The molar mass is 18.02 grams per 1 mole, always. Don't ever do that again. I know. People make that mistake all the time. And so this is the answer, okay? All right, I'm gonna let you go 3 minutes early. Hand in the HOD on your way out. And at home, oh wait, for a special problem, I'm gonna let you do 3B. And, yeah, 3B. What about 4? I didn't do.
That's the same as the, HOD. 4B is, yeah.
Oh, 3B and 4A. We didn't do 4A, right?
We did 4A.
Oh, all right. So 3B then is a special problem. Is that activity what? 3? 2? 2? Oh God, I can't even erase it.
You need a new pencil.
No, it's because I'm zooming and it's taking too much memory.
So are you not going to your office at all, or are you gonna be there?
I'll be there, right? I'll be there until 1:30ish.
Oh.
Thank you.
Okay, thank you. Oh. Follow signs for ignition.
All the way.
Circle the campus and go, as if you're going out to Mount Pleasant. We have a nice little left. That's already lost.
Yeah, so I would be honest.
Are you going there? Are you walking?
Put it in the pile.
So good. I'm gonna try to eat good, man. I know. You don't eat no games.
I want to show you how I was kind of doing the problems before I head out of here. I know you have like office hours and stuff.
Yeah, sure. I can do it right here because no one comes to this class. No one's in this room.
Oh, okay, that's cool.
There's nobody here, I think, at least a while.
No, 2 people said that they're going.
Oh, yeah.
I don't know if anyone else should go. So look, I was like doing it differently than how you were doing it.
See, sure, he can go here.
Oh, sorry.
You guys probably.
Okay.
Like it was working for a little bit.
Yeah, go ahead. I'm gonna be here for a few minutes.
Oh, I already handed in the handout of the day.
Oh, I don't know. It's all mess.
I did that.
You put it in here?
No, I didn't. I was gonna hand it in on what day is that?
Oh, yeah, hold on a minute.
Yeah, my fault, bro. I'll take that.
Yeah.
Ready?
I'm ready.
You might hate me. So the way I did this, like it was working and then it wasn't working. And then I kind of like checked what I was doing and it was like,
Yeah, why would you go through this trouble?
what do you mean this? You
Why
had to
would
write
you
this.
I don't get it. Why would you write this per 6 moles of water when you could use the 18.02 for 1 mole?
Because I wanted to like cancel out mistakes. But it's
What is
still the same thing though. I hear you, but that's not, I was gonna talk about this over here.
I don't like this. This is gonna get you in trouble. This is
Yeah.
too big. The calculations are too much. Well,
Well,
all
my
it does is,
calculator did it for me.
all right, I mean, all right, but it's just bad form.
Yeah.
Yeah.
So what I did over here, so I did like, they gave me the mass. So
Yeah.
I divided, like, I did like this section, this
Okay.
right here,
And you got 0.89.
and then 0.89 is the same thing over here, because it's 4 to 4. So I did this.
That's
And
not
then I
4 to
timed it.
4, it's 4 to 6.
No, on this first one.
4 to 4 for NO, but we're not finding
Yeah, so
NO.
I did that, and then I timed it by 1.5, and I got this number.
Well, you are really making life hard here.
What do you mean? And then you times that,
It's not involved. Why bring it in? Why go to
Because-
4 to 4 to 6, 4 to
because
4
then
to
you can
6?
get the ratio thingy. Ratio.
What is 4 to 6? Just plain, that's just.
Yeah, I
if you
know,
want-
but I
so
got
why
that.
didn't you just multiply this by 1.5 to get here? Why did you go through this thing? This doesn't make any sense.
No, yeah, you're right. I could have skipped the step. So I did that, and I got this number, and then I think I timed that by this, and I
Yeah.
got this.
Of course, yeah, it's the same thing, but
Yeah, so I could do it like that.
no, I want you to do it like this. You can, I mean, it's not wrong, but
Yeah, because I got the same answer. It was like,
But you know, why are you doing more work?
what do you mean? If I find this, I could do the problem for anyone. Like if I find this ratio, you know what I'm saying? I could find, like, if you wanted me to get like NO, I
It's
could have found that.
easier. I just don't get it.
This took me like 2 seconds. This took me like a whole minute to do this. You know?
I'm not gonna fight with you.
No, no. So that's like how I was doing it, but then it kind of like, it got confusing because I was trying to find this number and I
This is a
didn't know
lot,
how to
this
get
here's
that.
a lot of extra work. It's gonna be a time when the numbers aren't gonna work out so nice, but you know.
Yeah, so nice, yeah.
Yeah, like what if this was 5 to 4? Like what would you, I guess that's not so bad either, but
It's
like
1
5 to 2, I mean. Sure, I mean, you know what you're
Five.
doing. You're good at math, so go ahead, do it the way you want, but
Yeah.
if you get it wrong, it's not my fault.
I got you. That's fair. And so like even like up here, I was trying to do it over here, and I just like it was a bit harder. But I guess you could just divide this by 2, huh? It'd be 1.2.
Wait a minute now you have 50, so did you convert this to grams first? Yes, you did.
Yeah,
Okay, so it was 2.4 grams, I mean moles? Is that what it, because I don't know what you get here when you,
I think.
no,
2.
it's not, no.
I
No,
think
it's 1 point
1.8,
something.
1.8. Like a 1.8.
Yeah, okay, you're not even keeping the sig figs. You're never gonna get the sig fig right doing this.
Yeah, I know. Yeah, that's what I realized when I did.
And this
I
is
did-
not right either, should be 32.0, but then it'll give you. I mean, okay, so what did you put down for your answer then?
I stopped doing that one. I got confused, so I stopped it.
Yeah, you're getting confused because your way is confusing.
Yeah,
So use my way.
but I guess I could have did like, what is it? 2.4.
Look,
times-
David, when you do it my way, where's my way?
Okay.
When you do it this way, you know. You just do one calculation at the end, this times.
Yeah, you do it all in one
And
calculator.
this is just 18 and this is 1,
Yeah,
and it's,
same thing.
I mean, you don't, and this isn't right, by the way, it'd be grams, not grams per mole with mole, it'd be grams for 1 mole. That's 17.04 is grams per 1 mole.
Heard you.
Yeah. Anyway, you know, you can have shorthands for this. It could be just 6H2O to 4NH. You have your own little shorthands, but I recommend doing it that way. I
Yeah.
mean, you did this calculation. It's not like you avoided it.
No, I know how to do it. Yeah, but I want to find a way to like speed it up a little bit. I don't gotta like, I like shortcuts, you know?
Well, you know, if they work for you, it's okay. You get the right answer. But I'm gonna go crazy when you start trying to figure out if you make a mistake. I'm not gonna know where you made the mistake.
Yeah.
I'm not gonna say, oh, You got this right, but you got the stoichiometric ratio wrong, and then I take off a
The
certain.
whole point. Yeah, yeah, yeah.
No, I mean, if I don't know what you did, I can't give you partial credit.
Yeah, I know. Yeah, that's how I was looking on my quiz and stuff. Like you wrote all over my quiz, show your work, whereas,
I took off it though. Next time I might.
well, it's because I got the extra credit questions. I think
Yeah, you got a 10 anyway, right?
is that it? That's not
No.
it.
No, it has other stuff attached to it.
These are all my special
Longer.
problems. Hold up.
It's longer, it has those tables attached, right? Maybe not.
Right here.
No, it doesn't attach.
Yeah.
Yeah, I'm keeping track of how many special problems I guess. Right.
Yeah, here benefit of the doubt was given, but yeah, I did take off a little bit. But you got it back.
Yeah, I got it back. Yeah.
Did you get my email?
Let me head to the fucking. Thank you for taking time.
I still got to do that lag for.
You didn't do the lab report? Not yet. You want me to send you one?
No, don't do that.
No, just so you can take a look at it.
No, that's bullshit.
No, I don't do. No, David, I
No,
don't.
I sent it to the wrong professor.
That-
No wonder you didn't answer.
It's not that
See
hard.
what happens with my
Oh.
ocean brain. Cause I had a
Just
question, I was like, that's weird that she didn't
Yeah.
answer, cause I was just like, I'm really confused
Make
with
sure you
this
don't
one.
put, I'm talking to myself, make sure I don't put like.
So it kind of made more sense today,
Stuff.
because you did the moles and grams and stuff again, which is why I was confused with, because I kept getting confused with the back and forth.
Do it, I went last.
Oh, you do legs? I have to go do legs right now. I have to go
Yeah,
squat.
forget about it.
I hate squatting, no.
Careful. Don't hurt your back.
Yeah.
So I struggled a lot with finding this, and I only know it's two because there's two.
That's because that's how you know it.
But there's also
Oh,
a way.
hold on. So this is how many moles. What? I don't know what the moles.
So a sample of water weighs 35.17
Oh, yeah.
grams, and then it had three different questions, and then the last question was do it all. But I couldn't figure out how to set this one up, but then when you did it today,
Two
it
moles
makes
of
sense.
H for 1 mole
Yeah.
of H2O, right? So then the moles of H2O are canceled. Right, so the next.
Yeah,
thing
that's
is
usually what I
two
was
moles
going at.
H, 1 mole.
Like,
H2O, mole
like,
H2O.
it's really good.
Smoke ones? Yeah, hell yeah, dude. Yeah, why?
Heard that before.
It's gonna be like.
Yeah,
vanilla,
so
like-
how would I set that one up?
I'll put them on anyways.
Well, you start with this.
Yeah, I might have to go.
I wrote this guy an email and it's not true. I can't do
No,
that. Oh,
it's not like the speed dog goes out. Those ones are gonna do it.
I'm sorry.
Yeah, regular. It's like the whole class.
It's like, I know it's two because I know it's two, but like, I wanna know how to get the two, if I didn't know it was two.
Well, but wait a minute, but you know it's 2 because it's
Yes.
H2O. So there's 2 H's per 1.
Yeah, but then when the
Sounds
problem
hard.
asked down here to do it all together, I
think
didn't
it-
know what to write because I didn't know what the,
But that's a requirement.
or did I set that up right?
Here, you know, because it's 2 moles of H per 1 mole of H2O. That's what this is here.
Everything they're gonna reteach.
You understand that?
Yeah,
So
It's building.
it's just, I don't understand the
Yes.
question. really.
I like stared at this, so I'm like, how do I get two? I know I had two, but how did I get two?
But still.
You got it from the formula.
And then how can I come up with this thing when you have a problem like that? Sometimes I have a problem knowing what it's asking me to do. Like, it made it easier today when you had that written.
Grams to moles, I don't know, if it's just grams to moles of whatever you're given. This is, you're given grams of something. It's the grams of the something to moles of the something. The same thing, right?
Of the same thing that I have
Yes.
in grams.
2 moles of H to grams of H, right? So it's whatever you're given, that's what you have to, you're given grams of that thing, you find moles of that thing.
And then that I'm gonna
And then you
use for
connect
the
that
whole,
to, with using the mole
The
ratio for the
H2O.
reaction.
and then for the mole ratio, I do the molar mass.
No, the mole ratio is from the chemical reaction. It's the stoichiometric coefficients.
Okay.
So, okay.
So it would be 2 to 1, okay.
If it's a reaction, okay?
Yeah.
If it's going from grams of H2O to grams of hydrogen in water, right? Then it's going from moles of the water to moles of the hydrogen in water. That's from the formula. That's it.
Wow, most of the hydrogen in the water, okay.
Right.
And then I'm gonna change that to grams of the hydrogen.
At
to
the
get-
end, yes, yes.
Okay, let me email you this again, because I don't know who I emailed it.
I was wondering how I could practice polarity and dilution, because I was a little kind of confused.
There's some problems in, one of the activities, this chapter.
And so am I right in saying there, I know MCVC is like that part of it, like I understand how to plug in, but I don't understand like the part before that. Were we doing things with like mass by percentage, or is that
No,
different?
that's different. Anyway, this activity, 4, 6, and 7 is more problems of that kind.
Okay,
Oh,
okay, I can try to. Because that'll all be on. the exam, so
no, I don't know if it will.
Oh,
It might be. Yeah, I think so.
okay, I wanna get pretty familiar with it, so. I feel good about it, but I didn't know where I could practice it. Because the one that we already did, I guess I could erase the answer and stuff. I.
Yeah, the back of the book is gonna have some of those. I think
Okay.
I don't know if it's the humans or the odds that they have the solutions to.
Oh, okay,
It's one or the other. I
Okay.
can't remember which. Could figure that out.
all right. Okay.
You too.
Someone left this.
No, it's from last time.